Okay, we're going to solve some differential equations. And these are not super difficult. They do require just a little bit of careful thought. Well, it's nothing you can't do if you're just being careful. So they're both initial value problems. And the first one is going to be dp dt plus p equals 10. And then our initial condition is that when t is equal to 0, p is going to be equal to 4. So the main strategy here is to do separation. That's not how you spell separation. Separation of variables. And we would call this differential equation separable, because we're able to get it into some sort of thing where we can completely separate the variables and then integrate both sides. So in this case, we can't immediately integrate because we have this troublesome plus p, but we can move the p to the other side. And so we have dp dt is equal to 10 minus p. So now we can treat the 10 minus p kind of like a single unit, and then divide both sides by the 10 minus p to get all the p's on the left. And then we're going to multiply both sides by dt to get all the stuff in terms of t on the right. So once we do that, we have dp over 10 minus p is equal to dt. And so, and if this is difficult to visualize, this is the same thing as just 1 over 10 minus p dp. So I can write that out when we decide to integrate. So now we can integrate. So it's really just 1 over 10 minus p dp equal to the integral of dt. Now, to anti-differentiate this, there's different ways you can approach this. Depending on how experienced you are with taking antiderivatives, you might just immediately recognize, oh, well, that's just the negative. You can do the chain rule quickly in your head. If you can't, that's fine. There's a little trick that's super, super helpful to know that I'll show you. And it takes advantage of the property that if you have a minus, so two numbers subtracted from each other, the same thing as if you were to negate this, you just flip the order. So b minus a, and you negate. So what happens is we're going to multiply the top, the inside and the outside by -1, and then we'll be able to flip it around. So negative the integral of 1 over p minus 10 dv. So pause the video if you need to just take a moment to verify this algebra in your head. This is just an algebraic step. And the reason why we're taking this algebraic step is because the way that we've defined, essentially, so the integral of dx over x, this is just the natural log of the absolute value of x. And so we're trying to get it into a form where we can have the variable positive and out front, and then just here's a constant that's kind of irrelevant. So this is going to equal dt. So now the integral of 1 over p minus 10 dp is just the natural log now of the absolute value of this denominator. And then we happen to have this negative sign out front. So the natural log absolute value, here's the denominator, p minus 10. And then this net minus sign is just coming from the fact that we took that one algebraic step. And then this is just going to be t, because the derivative of t is 1, so 1 dt. And we need our constant. So from here, there are two equally valid ways to solve the problem. And depending on what you're more comfortable with, one might seem easier or one might feel just more straightforward than the other. So I'll leave that up to you to decide. I'll just do both ways, so you can see how you might go about solving the finishing off the problem from here. So from this step, the first way is to immediately use the initial condition. Okay, so the first strategy is if we immediately use the initial condition, to find the arbitrary constant c, so we don't have to worry about that. So in this case, that was if t is equal to 0, p is equal to 4. This is how, this is equivalent to the statement that they gave us, p0 equals 4. So let's plug that in. We have the negative natural log of absolute value. Now p is 4 minus 10. And then t is 0 plus c. Okay. Now, 4 minus 10 is really minus 6, right? But this is absolute value bars, and that's why the absolute value bars are very, very important. So it's actually just 6 once we do the absolute value. So we have the negative natural log of 6 is equal to c, right? Because 0 doesn't do anything. So this is our value for c that we can then plug back into here, into this step. So the negative natural log, now we don't forget those absolute value bars, they're very important. They're actually the reason a lot of people lose points because they seem insignificant, they seem like they don't make a difference, but once we finish both of this solution and the other method, you will realize how actually important they are in determining the correct solutions. All right, so then we have t minus natural log 6, because plus c, I'm adding this negative natural log 6, so it's subtracted there. Now we're isolating for p. So once you get to this point, now we just isolate p, because then p is ultimately what we're looking for, solution p equals something. So let's get rid of the negative by multiplying out by -1. So if we multiply this side by -1, we really just have natural log 6 minus t, because this will become positive and this will become negative. So it's just looks nice. So I'm going to take it over here. We can exponentiate. So in other words, exponentiate like that to cancel out the natural logs. Do not forget, after you exponentiate, to keep this in absolute value bars. You still haven't gotten rid of the absolute value bars when you exponentiate. So now e to the natural log 6 minus t, this is the same thing, and this is an algebra rule you just need to know backwards and forwards, is that this exponent rule, these are the same. So if you have the same base raised to different exponents, it's the same thing as just adding those exponents together. But this helps us simplify this, because now that specifically cancels and just leaves you with a 6. So if that step is confusing, go back, rewatch it, pause the video, think about it. And here I'll quickly reference the exponent rule in case you've forgotten. It's that if you have some number, doesn't matter what, raised to a certain power, and if you multiply it by the same base and a different exponent, it's the same thing as adding the exponents together. So here, natural log 6 plus a minus t gave us natural log 6 minus t, because e is the same base. Okay, so now we're going to do the step where we get rid of the absolute value bars. This is very important. When we get rid of the absolute value bars, now we're saying just p minus 10. What we're really saying is this has to be plus or minus whatever's on the other side. So we always say plus minus, and then the other side of the equation. So 6e to the minus t. Because since it's absolute value, p minus 10 could be actually negative, and then it was just made positive. So we got to account for that by saying plus minus over here. And now we can isolate p completely. So p is equal to 10 plus or minus 6e to the minus t. Now, we're almost done. We have to do one clarifying step to finish off. Is it plus or is it minus? It clearly can't be both, right? And that's why they give us the initial condition, because now we can verify. So let t equal 0. Let's just plug 0 into here and see what happens, right? So if we were to plug 0 into here, we would have 10 plus or minus 6e to the 0, and anything to the 0th power is just 1. So this is the same thing as 10 plus or minus 6. What is this supposed to equal? Well, given our initial condition, when t is equal to 0, p is supposed to be 4. That can only happen if we're using the minus here, 10 minus 6. Because if it was 10 plus 6, 10 plus 6 is 16. And I can guarantee you that 16 does not equal 4, right? 4 equals 4. So we need to use minus 6. 10 minus 6, not 10 plus 6. So we're using the minus side of the plus minus. So then our final solution, I ran out of space here, so I'll just put it right here. So p of t is, and I do this to just clarify that we did solve p as a function of t, is equal to 10 minus 6e to the minus t. Never hurts to just double check one more time that we have the right solution. If we were to plug in t equals 0, we would get 10 minus 6 times 1. So 10 minus 6 is 4. And look at that, we get back to p equals 4. So everything checks out, and this is the final solution. So you might be wondering, what was the other way to solve the problem? And the other method that I'm about to show you, and the reason why I show it second, is because when you're given the initial condition, this method is actually kind of preferred in my opinion. It's a little bit quicker, a little bit more straightforward. However, if you weren't given an initial condition, I would recommend this method because it's a little bit more general, it's a little bit more abstract, and it's just overall a little bit stronger for that kind of context. So instead of immediately solving for this arbitrary constant c, what we're going to do is wait. We're going to use the conceptual idea of what it means to be an arbitrary constant. So we're going to start by just immediately isolate for p. So the first step, instead of substituting, is isolate p. And a lot of the algebra is repeated, so I'm not going to explain it as deeply, but multiply by -1 on both sides. Now, why would I write plus c again, right, instead of minus c? Well, if you think about it, c is what? C is an arbitrary constant, which means it can be literally anything, and it doesn't matter. So it's the exact value of this constant truly doesn't matter. So if the difference between that constant times -1, which is just another, technically -1 is an arbitrary constant. So you have arbitrary constants, it's just an arbitrary constant. So we just leave it as c, we don't bother with it. Exponentiate. So we have absolute value of p minus 10 is equal to e to the c, e to the minus t. Now you might be wondering, how can I justify that step? Well, that's because I've done hundreds of these problems. If you need to justify it, go do the algebra on the scratch work, right? E minus t times e to the c, because this is the same thing using the exponent rule. And then I just flipped the order because multiplication is commutative. Okay, now if we take away the absolute value bars, again, so important, we plus or minus this because we're taking away the absolute value bars, so we need to account for that in full. And then we add 10, so 10 plus or minus e to e, e minus t. Now, here's the catch. We know that plus or minus, okay, so we know that plus or minus e to the c is just one number. So see this as just one number. I know it looks like a lot is going on. This is truly, at the end of the day, just one number because we've taken an arbitrary constant and made it the exponent to an arbitrary constant. And then we just chose its sign. So this is just a single number. View this as a single number, even though we're technically using, 3 symbols to denote just one number. We're going to solve for plus or minus e to the c. And a lot of times what you'll see in textbooks is they'll say, assign this number to just a random dummy variable placeholder for now. So we can do that. So that reduces the equation to just 10 plus a e to the minus t. Now we use, once we've isolated p, we use the initial condition. And that's going to be, again, t equals 0 and p equals 4. So 4 equals 10 plus a, which remember, a is just a stand-in right now. We haven't introduced anything new. A is just standing in for this blah number. And then e to the 0. Well, that's just 1. So a times 1, this is just 1. So we have a is equal to 4 minus 10 is equal to minus 6. So when we plug that back in, pt is equal to 10 minus 6 e to the minus t. You get the same exact answer using a different method because math works. So as long as you're following all the rules of algebra, you'll be fine. Okay. So that was the first problem. The other problem we're going to do is also kind of similar in that there's multiple ways to see it. There's actually 2 ways to solve it. They're both correct. And just depends on which one you like better. So it is dy dx is equal to sine x squared with the initial condition y of the square root of pi is equal to 4. Now, let's just do this by, again, let's separation of variables. So dy is equal to sine x squared dx. We just get the dx's and stuff over there. Now we drop the integral bars. Sine x squared dx. And we integrate. So y is equal to, now note something. You might be thinking, big red flag, we have no idea how to integrate this. Is it even integrable? Here's something. We cannot find a nice clean antiderivative, and that's fine. You can actually still answer the question in terms of the integral form of the antiderivative. So this conglomerate thing represents the antiderivative as if we were able to make it something cleaner. We just leave it that way. It's fine. And then we have a constant of integration, because that still comes, we did do an integral, so we need to account for some constant of integration. Now, there are two different ways to substitute the initial condition. There's two different ways. Sometimes one is better than the other. I'll show you the one that's going to be easiest conceptually first, and in terms of you being a Calc 1 student or Calc AB/BC student seeing this for the first time. It's to just simply plug in what we know. So it's basically, we're being told that x is equal to the square root of pi and that y is 4. So if we substitute those values in exactly where we see them in the equation, and then note that I'm too lazy to write this out, but if you have the square root of pi as x and then you just square it again, you get pi. So sine pi dx plus c. Hopefully you all quickly see that sine pi, well, that's nice because that's just 0, right? So 4 is equal to the integral of 0 dx plus c, and whatever 0 is, doesn't matter. It's just gonna, the antiderivative 0, 0. So c is going to be 4, meaning that we can write the final solution y as a function of x is equal to the antiderivative of whatever this is, so whatever that happens to be, plus 4. And this is a perfectly acceptable solution. Now, what's the other way we could have plugged in the initial condition? And this way seems really, really unnecessarily kind of complicated or long-winded, but it's genuinely conceptually not. And it's in my opinion, it's a little bit more airtight. So what we're first going to do is we're really going to remember by the Fundamental Theorem of Calculus, right? We're going to see as an accumulation function. So y is a function of x. We have the integral, and it's some constant a to x, the variable. That's important. These two variables right here and right here need to be the same. Now we can't reuse the variable x in here because we just used it. So we just got to do something to stand in, what we call the dummy variable. We haven't introduced a new variable. We just need something, a symbol to stand in conceptually for this antiderivative. So we often use t. T is kind of conventionally what we use, plus c. And so now we're going to strategically choose a such that when we do plug in the initial condition, this definite integral just goes to 0. And that happens when this equals this, a equals x. So when a equals x, you're going to get the definite integral to go away to 0, and then we'll just be left with c over here, and it's all great. Well, x is the square root of pi. So let's do that. So we say y x, the square root of pi, and then the square root of pi sine t squared dt plus c. And note that the y in this case, I forgot to write it down, is just 4. Well, again, c equals 4 because this is just going to go away to 0. So we do end up getting back. Now, what's kind of cool is you can get a slightly more precise answer. You can actually write that y of x is equal to the integral, the square root of pi to x, and then we're still using the dummy variable sine t squared dt plus 4. And so this is also another way you can do it. I personally like this one better because we got kind of lucky. If you think about it, the fact that this sine of pi got to 0, because most times that's just not going to happen. So highly recommend using this method instead. So there you have it. That's some. If this is your first course in calculus, these will be considered more advanced differential equation type problems with initial conditions. And if you are taking a college level differential equations course, there should hopefully be some review or like a unit 1 level stuff. So, thank you so much. Hopefully this was helpful.